So let's go ahead and get started with everything. So chapter 27 was talking all about our definition for current and how things actually move in charge, right? And actually it wasn't even about current when we started. It was actually about what happens when we take conductors, things that allow charge to move freely through them, and put some potential difference on them. Before that, we'd always assume that there was no potential difference on them. They were always equal potential. We just loaded it up with some charge and let it sit for a little while, then it'd be at equal potential. But what happens if we attach a battery that continuously has some sort of potential difference for those things? That is when we get a flow of charge, current, right? And so we talked about conventional current and electron current and how they're technically backwards from each other because we had circuits and conventional current figured out before we knew what electrons were. So this is an issue that we kind of continuously run into in not just physics, in all the fields that use electronics. We deal with it. But we said it's fine because technically speaking, negative charge flowing clockwise is the exact same as positive charge flowing counterclockwise. Effectively, they're the same thing. So all of our equations that already describe circuits very well still work just fine. We didn't break anything. Everything's all right. But we defined those two things, and we understood what current was, and then we understood what resistance was, and now we're going to tie this all together. Chapter 28 is all about practical battery resistor and sometimes capacitor circuits. So, in all of this stuff, we're going to have a lot of different pieces that we're going to need to keep track of, right? So here's everything that we're actually going to look at for this one. There are, of course, plenty of pieces. There are transistors, and there are op amps, and there are diodes, and all sorts of different crazy things going on. But we're not going to worry about all those things. We're going to focus on the simpler pieces of circuits, and these are what we're going to be expecting to see. We've got stuff like the battery, the wire, resistor, the light bulb, which is technically just another resistor. It's just a resistor that glows because it gets really hot. So that's really the only difference between a light bulb and a resistor. A light bulb is a resistor, as long as we're thinking about incandescent light bulbs. LEDs don't quite fit into that same thing. Fluorescent light bulbs don't fit into that same thing anymore. Both of those are a little bit different, but old classic incandescent bulbs are just resistors. We've got our good friend the junction that we saw last time. That's what happens when one wire forks out into multiple paths or forks into one path. We've got our good friend the parallel plate capacitor. And then finally we've got the switch. And the switch's job is to either open the circuit or close the circuit, let current through, or stop the current from going through. So these are all our cartoon kind of pictures of these pieces, but underneath them is a diagram symbol for each component. So what we're going to start doing here is not necessarily look at every single one of these as pictures like this. This is kind of complicated to look at, and we're going to realize why. If you haven't dealt with any circuits before or anything else like this, looking at the actual configuration of how the wires are going around can get very complicated. And on top of that, it's not always practical to draw, right? Because this has all of this detail, whereas an equivalent circuit diagram effectively does the exact same thing, but in a lot shorter manner, right? This is very simple. This is just like quite literally black on white kind of picture here. There's nothing complicated about labeling the resistors or the battery or showing how the wires connect or anything like that. It's just a bunch of lines, and that makes this a lot easier to draw. But anyways, each of these components has a symbol that represents them. So I know we've talked about sources of potential and how a battery can be that source of potential so far, but we've got a special diagram for this, right? And then the positive and negative imply which end of the battery is positive and which end of the battery is negative as it's connected in the circuit. If that is not on the drawing, that's okay. Look for the longer line. The longer line up top tells you which side is positive. Wires are just shown as straight black lines, nothing crazy about them. Resistors are squiggly black lines, right? Or zigzag. A light bulb is sometimes just drawn as a resistor because it is a resistor. But sometimes if we're implying that a resistor will glow brightly, then we'll use this symbol instead, but it's just a resistor. It's just another way to draw a resistor because sometimes we'll use resistors and light bulbs in the same circuit, so We sometimes differentiate them, but not always. The junction is just multiple lines coming off of one path, essentially, right? If I have my first path coming in and it breaks off into two other paths right here, that's a junction. Capacitor, very easy to see. It's two parallel plates, so that's how we draw it. And then finally, the switch looks something like this. The little dot tells me that it goes either up or down, and that's whether it's open or closed. So, and this will all get a little bit more, you'll get more used to this with a little bit of practice. But the reason that we like to draw these diagrams again is because it's much simpler to visualize. It's really easy to see this. It doesn't require you to have all the pieces in place because there's multiple ways I could do this. Whether I have the physical components, or if I put it in a breadboard, or if I have it on an integrated circuit, all of those things could look completely different. But the circuit diagram would always look exactly the same. So it's easy to model out what a circuit's doing if you just draw out the circuit diagram. Now, when I'm talking about putting components in the circuit, there's one of two ways that I can put them, right? If I have multiple components all together, I can either put them in series or in parallel, and the name really says it all here. In series implies that all along one path, I have each of the components. So if I put one resistor and a second resistor and a third resistor and a fourth resistor, and they're all along the same wire, those are all in series. They're all consecutive pieces in the path. If I look at the picture that I've got here on the slide, I have essentially, so here is some current coming from the battery. It's a junction, so it splits off down each path. That means the resistor and the capacitor are in parallel together, right? Parallel means that they are separated, two separate paths, or three separate paths, or four separate paths, but separate paths, and then they all recombine somewhere else down at the bottom and come back together. But we'll talk about that. We'll have some more pictures for that next time around. So, when we're talking about dealing with any of these circuits, drawing these things out, solving circuits, understanding everything that goes on about them, we actually only need two rules. So these are called Kirchhoff's laws. And there's the loop law and there's the junction law. And the junction law you've actually already talked about, right? It just hasn't been under the name Kirchhoff. It's been under the name conservation of current. If I have any sort of junction, if 100 electrons come in, 40 electrons leave that path, then we know 60 electrons are going to have to leave the other path because 100 came in, 100 have to come out. So anytime I have a junction, the current coming in has to equal the current coming out. If I sum up every single path that each of those could have, all of them have to sum to equal together again. So let's try that out. Whiteboard 28-1. I have essentially some little corner of the circuit. I don't know what's supplying these things, but what's being implied here is I have a resistor coming into a junction right here in the middle, goes down to another resistor and then off to some other wire. Who knows what's on any end of these things. So this picture is a little bit strange, even if you've seen circuits before, because this notation is just a little bit weird. What we're saying here is that we see that, so they're squiggly lines, they're two resistors. The resistor is 2 ohm and 5 ohms. The potential difference over this resistor is 4 volts. The potential difference over this resistor is 15 volts. And the direction of that potential difference, it's higher on this side and lower on this side. So I just want to kind of draw your attention to that, make sure that's understood what that's trying to say here. But anyways, we know what conservation of current looks like. We also know that current is going to flow, conventional current will flow from positive to negative. So what I want you to do for this problem is to draw out what all three currents, what you think they're going to be. You don't have to be correct, but take a wild stab at the direction of all three of these currents. And, well, for these two, we should know, because if it's going from positive to negative, this current looks like this, and this current looks like this. So take a wild stab at what I could be. It doesn't have to be correct, but then I want you to solve this out as a conservation of current problem. And depending on what you get at the end will tell you whether your guess was correct or incorrect. All right. How's about we start taking a look? Okay, So at the very beginning, I already said what direction the currents should be going, right? And just to kind of justify that again, the more of the two positive potentials is going to be where the plus sign is. The more negative of the two is going to be where the minus sign is. Conventional current flows from the positive to the negative. So I'm expecting this. I'm expecting this. And I'll label these. So this is I top. This is I bottom. And I'm just going to leave this one as I. Okay. So now what I said was take a random guess. You don't have to for this problem, but we're going to find that in a lot of these circuit problems, we have to get used to taking guesses with what our current is going to be. And I want to try and introduce that as early as possible here. So what I'm going to do is I'm going to take a random guess at this thing, and I'm going to see what happens. I'm going to take a wild guess that my current goes like this. Maybe I'm right. Maybe I'm not. Let's see what happens. My conservation of current at this junction right here tells me that, okay, all of my input must equal output. Okay, so now that I've got that, well, I'm looking for I. If I could find that, that'd be fantastic, but I don't have everything yet. I need to find I of t and I of b first. So what I'll do is I'll say, okay, well, I know what the potential difference is. I know what the resistance is. I have enough information to find the current through each resistor. We will use our handy-dandy equation. I asked for that to be in gray, please. Thank you. I is equal to delta V divided by R. So for the top one, I of t is going to be equal to 4 volts divided by 2 ohms. I of b is going to be equal to 15 volts divided by 5 ohms. Okay, now that I've got these two, I come back to my conservation of current equation, and I say, okay, well now this is 2 is equal to I plus 3. Something's weird here. This implies that the current is negative 1 amp. So I'll ask chat on this one. What do we think this means? What does it mean that I have a negative 1 amp for my current? Any guesses? More generally than that. More generally than going into the circuit, it just means that the direction I guessed is wrong. And that's not a big deal, because the magnitude is the same. It just says, this says actual current. Actual current is 1 amp to the left. That's all. And there's so many extra dots. This is driving me crazy. I thought fixing the driver would help this, but it's a little bit better. So yeah, all that's really saying is that this right here, this was my guess. This is the actual. Now, I am not going to change my guess. If I would like to actually draw this again, I need to either use a different color to differentiate it, label it like this, or draw a brand new picture with the correct current. Because think what happens if we go halfway through, if we get to partway through into our problem, and we say, oh, I guessed wrong. I'm about to get a negative answer. Let me flip that. What happens now? Our equation that we started with is now backwards. Any work that we have done from the beginning of the problem is now invalidated if you flip it too soon. You have to guess something and commit to that guess until the very end of the problem. At the very end of the problem, and I mean the end of the problem, then you can determine what directions the current should be going. But anywhere before that, you have to commit to the guess that you made. And that's totally fine, right? Because what we just found is the only difference is a negative sign. But if we have a problem where you're asked to find 7 different currents, and there is a problem where you're asked to find 7 different currents, you can't find current number 4, decide that you've drawn one of them wrong, and then flip it. Because now all of your answers, everything that you've just written has to be rewritten because the entire format has been changed. Commit to a guess, solve the problem, fix it at the end. That's the methodology here. And we'll do this a couple more times before we dig all the way into this. Then let's keep moving along. So, the first one is one that we have arguably seen before, right? Conservation of current was from last time. The new one here is going to be what we're sometimes going to call the loop law. Here's the idea. Pick a start point in a circuit. If I follow a path all the way around my circuit, so I go through this one, I pick up a potential difference V1. I go through this one, I pick up a potential difference V2, V3, V4, and I come back to my starting point. There's an important feature of potential, is that it's path independent. It comes from a conservative force. The potential at any point in space is determined by everything else around it, and it does not depend on how you got to that particular point in space. What I'm trying to say is that when we take this complete loop, when we look at the potential difference provided by each piece, whether it's a battery providing something, or if it's a resistor using something, or any component that we could possibly consider, once we get back to our starting point, the potential that we started with has to be exactly the same as the potential that we ended with. Otherwise written, delta V of everything is equal to 0. Now, if we go halfway around, all bets off. But if we come back to our initial position, if the total distance we have moved ends up being, if the total displacement at the end of the day ends up being 0, I shouldn't say distance, displacement. If the displacement is 0, then the potential could not have changed. All of the contributions that we have gone through making our loop sum up to be 0, which means that some of these are positive, some of these are negative, right? And we're going to expect to see that. But this is how we're actually going to handle all of our circuits. And I'm going to not even highly recommend, nearly demand that you draw out these loops. This is the way to do it. And it's anything else is just going to be a nightmare to deal with. I promise. Like from experience of solving these problems for a very, very long time, draw out these loops. Draw out these pictures. Please. I mean, I guess I can't force you to do it, but man, it's just, there's not a good way to do it otherwise. So, knowing this, knowing that each component is going to do something to the potential, let's look at the pieces as they contribute to it. First, we have the battery, right? Batteries are probably the easiest one to deal with here. Generally speaking, if we go from negative to positive, so let's say that my potential here is 0, not change of potential, but if my potential here is 0, the more negative of the two, then here at the more positive end of the two, I'm going to have a potential now of curly E. Why doesn't the current just flow from positive to negative? Well, batteries are a little bit strange. Current can't actually flow through batteries. If I'm being completely honest, this is one of the things that we kind of cover this up a little bit, but current can't actually flow through batteries, and that's the entire reason why they hold charge, right? You don't see batteries constantly dissipating energy and heating up because there's a separation. They've got a bunch of positive charge on one side and a bunch of negative charge on the other side. And it's only when you give them some path to go through that they travel around, right? But there's no way for those positive and negative charges to get to each other when they're still inside of the battery, which is kind of indicated by the fact that there are some gaps here, right? There are breaks between these two. You can't actually, there's no connection between the positive and the negative. So it has to have some external path for the battery to actually start moving charge. But that's the kind of potential difference it makes. If I flip this around, if I'm following a path and I go the opposite direction, if I go against the battery, as I'll say, then here was the more positive end, here's the more negative end, we are going to see a contribution of negative E instead. If you hold a battery's positive side and negative side together, is there current? No. Until you connect the ends. So, and this is kind of a fun thing. I didn't want to bring this up, so this is a perfect segue. You might notice in a lot of different devices. Let me rip apart this thing, actually. I've got a visual example for this. So, take a look at the back of this calculator. We've got 4 batteries that are all opposite the next one, right? It goes up and then down and then up and then down. So what's going on here? Let's talk about this. Well, the calculator is actually run on a 6-volt power supply. What I've actually got here, and what's not completely visible, but there are little tiny metal pads. Most devices you have probably have batteries in a configuration like this, right? Where one goes up, the other goes down. The reason being is because there's a tiny little metal pad connecting the positive to the negative. And if we stack a bunch of batteries, we're adding the potential, right? If we're following this loop around, I stack one so it's negative to positive and then negative to positive and then negative to positive, all 3 of those are adding to the potential. So if it's 3 AAA batteries or 4 AAA batteries, then I would have 1.5 plus 1.5 plus 1.5 plus 1.5, total of 6 at the end. If I were to flip a battery around, now I would have a positive to positive or a negative to negative. So if I'm following my loop, one adds 1.5, one subtracts 1.5, which is why your device won't operate if you put the batteries in the wrong way. And that's also why we stack these things this way, because this is actually how you build up voltage. 1.5 volts is not actually a voltage that many things run on, but 3 volts or 6 volts or 9 volts is a much more common voltage to see. So, it's kind of a neat feature, right? That's how we build up different voltages set up like that. And it's also why certain devices will take 6 batteries and you all stack them end to end. Right? You can't flip any of them because if you flip any of them, the device doesn't work anymore. Or maybe it will, but it's going to act really funky. So most devices run that way. I have seen on a very rare occasion, I used to have one alarm clock actually that had both batteries pointing in the same direction, but the reason being was because they weren't actually connected together. It was a really weird setup where one battery ran the clock, the other battery ran everything else with the alarm clock. So they were separate functions, and that was, I think, one of the only times I've ever seen both batteries go like that. Because otherwise, the easiest way to stack them without taking all of that space to vertically stack all the batteries is to just have a little tiny metal plate here at the bottom touching those 2 ends together. But even if I stack a ton of those, it wouldn't do anything until I complete the circuit somewhere else. Right? I can stack together as many batteries as I want, and in fact, that's what a 9-volt is. It's 6 1.5-volt cells, but it doesn't move any charge until I have something connected to those 2 ends. Then I close the circuit, then current's allowed to flow through. So, that's how batteries contribute potential. But I always imagine that batteries are essentially granting some potential, and then the resistors are spending it. So, if we are going along the direction of current going through a resistor, this is where I say it's spending that potential. It's a negative IR, gives me the potential difference over this resistor. If we're going the opposite direction of that, just in the exact same way, it's giving some back. Now the delta V would be negative of negative IR, or just positive IR. But these are the 2 components that we're going to see giving us some sort of change in potential, right? That's how we're going to see this thing from now on. These are essentially the 4 different possibilities you can have. Batteries in one way or the other, resistors in one way or the other. But what this depends on is you guessing what this current is in the first place. And again, if you guess wrong, it's not a big deal. It's expected. You're going to have a lot of problems where you're frankly not going to be able to tell. who knows what direction the current goes? So you guess, and then at the very end of the problem, you'll know for sure. Speaking of, here's another problem. Step 1. There's not multiple currents because there's no branching paths. There's only one current going through this circuit, but I want you to guess. Pick a direction. It doesn't matter. Don't look at the problem at all. Just guess a direction that the current is going to go. Then once you've guessed, draw a loop that matches that direction of current. Right? So if the current's going clockwise, make your loop go clockwise. If the current's going counterclockwise, make the loop go counterclockwise. Just make it match the current. And then solve out for this thing. And see what you get. Was your guess correct? Was it not correct? Either way. All right. How's about we start to take a look at this one? So let's go ahead and copy this thing over. That'll help. Because we're going to draw plenty on this thing. And now I know what the answer to this is going to be. And surprise, surprise, I knew the answer for the last one too. But I'm going to purposefully guess wrong again, because I want to just really hammer this point home that it doesn't matter what direction you pick. You just have to guess. So what I'm going to do is I'm going to say, hey, clocks run clockwise. I'm going to assume that currents run clockwise. That's a good justification, I guess. So let's assume that the current goes like this. Okay. Now I'm going to draw my loop to match that current. What direction I draw the loop doesn't matter either, but it's just a little bit easier like this right now. So as I go through, here's my starting point. I hit my 9-volt battery first. I start from the negative, I go to the positive. So I've picked up a positive 9 volts of potential. Keep going around this loop, and I hit my next piece, my resistor. I'm going with the current. The direction of my loop is going with the current, so that'll be a negative I times resistance, 10 ohms. Now we keep going, we keep going, we keep going. Now we're going against this battery. We're going from the positive end to the negative end, so that means we are going to be subtracting 18 volts. And I come around to the very end, back to my starting point. Nothing else in the way. Okay. Now that I'm back to my starting point, I know that everything should have summed up to be equal to 0. So, now that we've got that, let's start combining some things together, right? I look at this thing and I say, okay, I don't need a system of equations. I've only got one unknown. I can solve this problem here. So, the next step is going to look like -9 minus 10i. Rearrange it. So this will be 10i is equal to -9. I is equal to negative 0.9 amps. I guessed wrong. And I knew I guessed wrong, but that's okay, right? And I committed to this picture. I didn't try to flip it halfway through or anything like that. I wanted to commit to this picture the entire time. And now that I've done that, now I can say actual current is 0.9 amps counterclockwise. And that's it. That's where we get this one. But I've drawn out my picture, I've drawn out my loop, and I'm going to commit to that thing the entire time. I'm going to just stick with my picture until the very end of the problem. And then at the very end of the problem, once I have all of my answers, then I think about what the actual current should be doing. So, the resistor is negative because it's bending this. The way that the potential difference goes, it's coming from this. This is a little bit weird at first. But when you're going along with the current, there's a potential difference. If we go back to like our do I have one that's just a battery and a resistor? Let me look at just the battery and the resistor real quick. We're not to the slide yet. We'll talk about this in a second. But if I'm looking at just these two components, if I'm thinking about these things, here's where my description of I pick up a positive delta V because of the battery as I go around the loop this way. The potential provides me a potential, or the battery provides me a potential difference. The resistor spends that potential difference. So going along the direction of the current through a resistor takes away from our potential. This is the more positive end. This is the more negative end. There is a delta V is less than 0 for this piece. Now, my intuition with this problem probably should have been something along the lines of the 18 volt, they're pushing against each other, right? The 9 volts trying to push current this way, the 18 volts trying to push current this way, but the 18 volts stronger, so it wins. If there was another path or something, that might not be the case anymore, but my intuition would tell me that the current would be going the other way. But we'll build up that intuition as we go farther into this. As you get a little bit more experience with these problems, that makes a little bit more sense. But again, it's not a big deal. If you guess wrong, it's a negative sign. Who cares? So let's go ahead and look at the slide that I've got pulled up now. So the language that we have has already really suggested to us that power and energy are part of this, right? When the electricity cuts out in your house, you say the power's out. When the batteries run dry, you know, they're out of power, all of things like that. We keep using this language. So now here we are trying to really formalize, how do you actually describe power in a circuit? Well, I think we all generally know that the battery is the one supplying that power. That's the source of the energy in the first place. But what happens to the rest of it? Well, any power that the battery supplies that gets used up is dissipated somewhere else in the circuit. And this is exactly what happens with, think about the one big resistor that everybody has, the stovetop. That stovetop is just a really big low resistance resistor. It's got a wall socket instead of a battery, but it's the same idea, right? It's a potential difference being applied. There's a resistor, and how does it dissipate that energy? It generates heat. That's actually how almost all electronics dissipate heat, right? That's why your laptop has a fan inside of it right now, blowing out some of that excess heat. Anytime we're talking about using electricity, pushing current through different places, through resistors and diodes and all those things, all of those things are expressing that energy as typically heat. Sometimes as light, but typically heat. So I have technically two separate quantities, the power supplied and the power dissipated. If I had a bunch of different components, they're equal, but they're coming from different places, right? Because one is energy entering the circuit, the other is energy leaving the circuit. At the end of the day, when I disconnect the battery again, it still has no more energy than it started with. But while the battery's plugged in, it's dissipating that energy. So, power supplied, if I'm talking about a battery, the easiest way to do this is to say delta V times I, where I is the current through the battery. And that's a really important point. Through the battery. And I know I said before that current doesn't technically go through a battery. And that still holds true. Current doesn't technically go through a battery. Technically, what we have just drawn in this picture is kind of like a configuration you would see for rechargeable batteries, where you've got a potential pushing a bunch of positive charge onto one end of a battery and pushing a bunch of negative charge onto the other end of the battery. That's essentially, this is your battery recharging station. So technically current doesn't go through, but this essentially shows us what the power being generated by the battery is in this case. Power dissipated, I can write out in actually a few different ways, but we need to be very careful with this, and we're about to look at a problem that's going to exemplify this point for me. This delta V right here, delta V is not the power or the potential difference from the battery. It's not. This delta V is the potential difference over the resistor. Now, here, they're equivalent. But if I were to have a second resistor, if I add in a second resistor right there, so this is R1 and this is R2. Now, there's a delta V1 and a delta V2. Delta V1 plus delta V2 is equal to the delta V provided by the battery. But it's not the same. The two quantities sum up to be my potential difference because they're spending that potential difference. I have to come back down to 0 from where I started. But that's a really important point that I think a lot of people get mixed up on. You can't just plug in the delta V from the battery. You have to consider the delta V from the resistor. So I would probably actually recommend not using this one and not using this one. I think this one is probably the star of the show, because this avoids that issue. If you look at the current going through the resistor times the resistance, that is the easiest way to consider this. But it isn't the only way, and we can see that if it's only one resistor, this equation does a fantastic job. It's simple, but I want you to keep that in mind. Right? That is my big emphasis, though, that the delta V here is not the same as from the battery. These are two separate pieces, and we have to keep them separated. So, speaking on that, let's go ahead and look at our last whiteboard problem for the day. I have a circuit now with two resistors in it. So there's no worry about junctions or anything else. There's no current splitting up. But you have to draw out your loop. You have to guess what direction the current's going. You have to draw out the loop. You have to write down the loop equation. And then you've got to solve for what the current is going to be through this circuit before you can find the power. And then I'm looking specifically for the power dissipated only by R2, but calculate both. Okay, let's go ahead and start taking a look here. So we'll copy this thing over, we'll draw some pictures on it. Or I guess it is part of our picture, isn't it? So for this one, I kind of already know where it's going to go, so I'm not going to make a wrong guess for this one. I'll make a correct guess just to prove that it still gets us to the same goal at the very end, right? I'm not expecting to see negative signs for everything that I do, just occasionally. So what I'm going to say here, okay, current should go from positive to negative, right? And the current doesn't go through the battery, it goes out and about from the battery. So I'm expecting this to be pushing the current to go like that. So let's label that I. Current I wraps around clockwise. Okay, there's no junctions, nothing like that, but now I need to draw a loop. I'm going to start from this point right here, and the point that you start with doesn't matter at all. I could start from any point along this thing, but just here's a convenient spot for me. So now that I draw the loop, I'll draw it like this. So in order, positive 12 volts. Now we're going with the current through a resistor, so that's a minus 12 times I. With the current through the second resistor, minus 18 times I. Back to our starting point, equal to 0. Again, I don't have anything crazy going on here, right? There's only one unknown, so let's go ahead and combine like terms. 12 minus 30, I. Rearrange it. I is equal to 12 divided by 30. I get a positive, for the first time, 0.4 amps. So that should help, right? To make sure that everything still works in the end of the day. It is a positive current if we guessed correctly in the first place. But again, that's the only difference. Question. Because as I'm going through this thing, through the battery, I'm going from the negative side to the positive side. So if I said that V is equal to 0 right here, if I could use my device, if V is equal to 0 right here, we're starting at 0, we're going up to 12 volts right here. That's why it's a positive 12, because we're going along the battery in our loop. Absolutely. So now we know what the current needs to be. So now all we have to do is take that equation that we just had and use it. That equation being P is equal to I squared R. I can't use delta V squared over R. Because if I plug in 12 volts over 12 ohms, that's assuming that there's not a second resistor. It's not accurate. So we have to make sure that if we're using that equation, we're only looking at the potential difference over one resistor at a time, which makes this the easiest equation to use. Because it's the same current, then all we need is the resistor values for each one. So R1, or not R1, I want to label this as P1, power through the first resistor. Make sure that I'm back on this thing. Power through the first resistor, P1, is equal to I squared times R. Plug in 0.4 for I. Plug in 12 for R, R1 specifically. And when we plug that in, we should find 1.92 watts. If we do the exact same thing for P2, I squared R2 is equal to 2.88 watts. And let's check for ourselves real quick. So this is our final answer, but let's just ask ourselves, does the power dissipated match the power generated, put into the circuit in the first place? So the power produced by the battery, call this PB, will be equal to I delta V, where delta V is the potential difference of the battery. So that's 0.4 times 12. 0.4 times 12 is going to give me 3, or oh sheet, am I forgetting this number? 12 times 0.4, 3.6, right? Am I crazy here? No, that's it. Something's a little bit strange here. What did I do? I'm thinking through the math in a weird way. 1.92, 2.8. Oh, it's not 3.6. That's why. Jeez, I'm going to have a tough time trying to edit that to look like I know how to do arithmetic. 0.4 times 12 is not 3.6. It's 4.8. Maybe I'll keep that in anyways, though, because realistically, you guys should know that the math mistakes and everything else, it never goes away, right? I try to laugh it off every single time because I do the exact same thing, right? It's no worry at all. But when we put those two things together, the total sum of these together is 4.8. Power dissipated matches power produced. Everything is right. With that, we're actually going to close out our 28-1 lecture today. It's a little bit short. Next time around, it'll be another short one, but we'll have a lab to go alongside of it. So my plan here is that the lecture is a little bit short, ends plenty early, and that way you've got a little bit of time because the lab's a little bit of a longer one. So I'm not eating into too much of your time more than normal or anything like that. Give you some of the class time to work on that. To work on finishing up that lab, or at least getting a large chunk of it done. But next time, we'll start to look a little bit more in how we actually combine these things, another way that we could have treated this problem in particular, and what series and parallel actually looks like in different circuits. So this is actually our first example of a resistor in series kind of circuit, but we'll see what each of them looks like sometime later here.